Welcome, everyone. I'm very happy to introduce this very first talk in this series organized by the IAU Commission G5 on stellar and planetary atmospheres. We've been thinking about doing these talks for a while, and now we finally started. And as you know, the Commission is devoted to this topic of stellar and planetary atmospheres, and we'll try to have talks closely related to our interest on research, modeling, instrumentation, tools, anything. We aim to have a cadence of a talk every 2 months. First, I would like to thank my colleagues in the organizing committee of the Commission for helping with this, in particular to Daniela Korkakova, who's here, who has been the motor behind this initiative, and also Katia Cunha, part of the organizing committee, who has gladly accepted to lead the questions at the end of the talk and moderate the session, the discussion. It's really, well, also thanks to the ISC technical support for helping with this, and to the Commission leading the seminars at the ISC, who have helped a lot. And for the first talk, it's really an honor to have Professor Åke Nordlund with us. Åke started his career, well, he was born and educated in Sweden, did his master's in Uppsala and PhD in Stockholm. And he's spent most of his career at the University of Copenhagen, with long, frequent stays in various places in the United States. And he's a professor at the Niels Bohr Institute of the University of Copenhagen since 2004. And he's a very prominent figure and well-known in astrophysics in general for his important contributions to the field of numerical modeling, especially radiation, hydrodynamics of stars and the interstellar medium. And today, he's gonna talk about task-based computing and how this new technology can help us to make progress on the field of stellar and planetary atmospheres in particular. Please keep your cameras and microphones off for the duration of the talk. And Katia will later explain the rules for making questions. Okay, please. Welcome.
Thanks very much, and thanks for this invitation. So I'm going to talk to you about revolution in task-based computing, and especially its application to stellar and planetary atmospheres. We have also a totally different field of application, namely star formation, where the problems are basically the same, and I will point to the parallel. This is work done with a number of collaborators in various places, in particular, most of all, Andreas Popovas in Oslo, and Jonathan Ramsey in Virginia, and a number of people who are working on applications. So, is it really a revolution rather than evolution? Well, I'm going to illustrate these by taking a concrete example, so you can see that it's really not a small increment, but it's an important jump in performance. So let's take a concrete example, namely solar active regions, which my collaborator Bob Stein and I have been modeling for quite some time. And here is an example that serves the purpose of showing the problems and the solutions. It's a model of a solar active region of 48 megameters horizontal size and a vertical size of 20 megameters. Has a resolution of 2000 squared by 500, which currently is not a very impressive resolution, but it serves the purpose of illustration here. Solar active regions really illustrate the problem because we can't really think about them without thinking of the context. And these amazing structures that I will show you actually came about completely spontaneously. At the bottom of this 20 megameter box, we are feeding in a horizontal uniform magnetic field. That's all we do. We do not implement any flux tubes or anything. So the structures you see are totally created by the multi-scale convective flow, which transports both up and down, of course, conserving mass. And as it does so, it transports magnetic fields and creates these structures. So if we look at surface intensity, we immediately spot a small sunspot. And if we zoom into it, we see that it's of the order of 5 megameters on the long side and just a few megameters across. And here we can probably discern some structure even in the cold umbra. And this is the center of our attention, actually, but there's lots more here. So the horizontal magnetic field shows, of course,
Excuse me, Professor Nordlund. Apparently, people in the chat, they are saying that they cannot see, as we were commenting before, we can see a static screen.
Oh, really?
With no movement at all. So I thought you wanted to do some sort of demonstration, but apparently that's not the case anymore. What we see is some Python script. It's like a plot in the central panel.
Okay.
That's what we see.
Let's redo the screen share. Screen share. I come behind my other screen here.
We can see the same screen as before.
You still don't see this?
Yes, same static screen.
Amazing. Well, let me try another thing then. How about now?
Yeah, now we see a slide. Yeah, probably a proper slide. Yeah, sorry.
Okay. I'm sorry, I thought we had this sorted out before I started.
No worries, you can start any moment.
Right. So I was talking about these slides showing a solar active region. First of all, a small sunspot, which is of a few megameter size. And here we look at the horizontal magnetic field, which I hope you can see now. It spreads out, of course, from the spot. And if we look at the vertical magnetic field, it's both negative and positive. And you notice that it's very intermittent. So there are lots of patches, small patches with about 2 kilogauss plus and minus. And of course, the sunspot is dominating in one polarity. But there are lots of polarity of the opposite sign as well. And indeed, by construction, this has basically a zero average field. So if we look at the total magnetic field, it looks like that. And if we have the density on the other side, we have the 2 components that we really need to compute the Alfvén velocity. And it reaches actually 150 kilometers per second in this surface layer. So this is basically the optical depth unity surface layer. And the fast mode speed is essentially the Alfvén speed plus the sound speed in quadrature. And the picture in log speed looks like so. If we plot the maximum fast mode speed as a function of depth, this is what it looks like. And that's the big problem. It reaches 684 kilometers per second at the top layer, and you can see the trend. The trend shows that it would be even higher if you go higher up in the atmosphere, which you need to do if you want to model the chromosphere and the corona. And in traditional codes, this is a huge problem that only gets worse and worse because they use a simple domain decomposition to parallelize. We could, for example, imagine running this problem on 100 MPI ranks, where each one could be a socket, so maybe 20 cores or something. And then we would split this thing into 200 by 200 by 500 cells, perhaps, split it 10 times vertically and horizontally. And we would have 10,000 cells per core in this case. They all would have to update at the same time because each process needs a few layers from the neighbor, often called guard zones or ghost zones. And all of these processes would have to update exactly in sync. So the larger the problem, the larger this synchronization requirement becomes. The time step would have to respect this highest fast mode speed. And it means that the more layers we add, the smaller the time step would be. And it would be a huge waste of work because most cells hardly change at all with such a small time step. And a parallel problem arises in many other contexts. You could imagine, for example, a full galaxy, a simulation of a full galaxy down to individual star and planet formation. And it's actually doable marginally now on existing hardware. And then, of course, you have many semi-autonomous hierarchical regions of space. You would have giant molecular clouds, you would have spiral arms, and they're basically independent of each other. And nevertheless, each one of them would have to respect the very worst phase speed anywhere in this huge simulation. That's, of course, ridiculous. I can't work like that. And most cells would be wasting enormous amounts of computing time. So somehow being able to use local time steps would allow huge gain in effective performance. And I would also like to note in passing here that there's this often mathematical misunderstanding, or actually mathematical understanding, that self-gravity needs a Poisson solution, which means that it couples everything together. Of course, it couples really with the speed of light, but for practical purposes, that would be an infinite speed. That's supposed to be a problem because then everything must be coupled. But if we think about how things really work, when we think about, for example, the orbits of satellites near Earth, we don't really have to worry about the moons of Jupiter or anything far away. So these problems are really local problems also, if one just thinks of them like that. So now let's look at what we can do about this in the active region context. So we can take a look at the histogram of fast mode speed. And in the surface layer, as we saw before, it reaches 150 kilometers per second. But if you look at the vertical axis here, there are millions of cells that have a fast mode speed of only about 10 kilometers per second, namely the sound speed near the surface. And there's just a tail of a very small fraction of cells. If we convert that to time step, we see, of course, just the inverted histogram. So there are a small fraction of cells that require a small time step. And indeed, if we were able to use the average time step or the average fast mode speed, it turns out that the average fast mode speed in this figure is actually 9.8 kilometers per second. So these very high numbers don't enter into the average because they are so few. So here's the same plot again, showing the max fast mode speed in blue. And the green dashed line shows the largest fast mode speed. But if we're able to use the mean speed instead, then we reduce the cost of this entire simulation with a factor of 33 in this case. How can we do that? Well, we put them in a very large number of pieces that are much, much smaller, for example, of the order of 20 cubed instead of 200 by 200. And then we arrange things so that each piece only needs to respect the local Courant condition. And how can we do that? It needs still to have ghost zone information from its neighbors. Well, if the neighbors have a record of time slices, they can interpolate, or in some cases extrapolate, to give the task its guard zone information. So in the rest of the talk, I will explain how this is done in practice in the Splash code framework. And you may then ask, why is it called a code framework rather than a code? And that's what I want to explain also. So in this case, we will get about 250,000 tasks. That's many more than we have cores, and that's exactly the point, because each core needs to have work that can be done all the time. And in this case, when we split things into semi-independent tasks, they are not all updatable at the same time. Typically, just say 5 or 10% of them can be updated at any one time. And therefore, if we have an overloading of oversubscription of work for each task, it all works out and they can all be doing work all the time. So the code framework, why is it called the code framework? Well, it's designed to have unlimited scaling. And it's designed to have a perfect condition for the solvers in the sense that they're small, they're cache friendly, and easy to implement. And the background of this was a conference in exascale computing. So it's really an idea that's aiming for the exascale era, which is starting now really, because in the fall, the Nordic or Northern European HPC center in Finland is opening up. It's actually opening up in the summer, but only in the CPU part. The GPU part will be opening in late fall probably. And that will give us not an exascale machine, but probably as a Scandinavian as much access as we would get from competing on a world scene exascale machine. So we're right there, and we really have to be prepared for it. A public version of this code is available, and you can find it at readthedocs.io. And it has 5 key concepts. It has these local tasks that use local time steps, using the time extrapolation or interpolation, with roughly half a dozen time slices for each. It has adaptive mesh refinement in that it can create, as we can see in this illustration, subtasks that have a smaller cell and higher resolution down to an unlimited number of levels. It just costs extra, of course. Every cell, which is half as big, costs 16 times more. Since all of the cores always have work to do, this is perfectly parallel in terms of OpenMP, in terms of cores being able to find work. And the ideal setup is typically to have one MPI rank equal to one socket, because on a socket, the access to memory is ideally organized. If you use more than one socket, then memory contention will become a problem. In between the MPI ranks, it's perfectly MPI parallel because the MPI processes only need to talk to their nearest neighbor. So there's no need for a synchronized all-over communication. And this nearest neighbor synchronization is hidden from view in the sense that a request is made and a request is satisfied. And in the meantime, the core that makes the request can do other work. So there is no latency visible. Even though there is a latency, it doesn't cause any waste of time. It's adaptive in the sense both adaptive mesh and adaptive physics, and it has mesh refinement and method refinement. And the point is to call it a code framework because it can accept any type of solver. And you can have different kinds of solvers acting at any one time. So we have, for example, implemented some solvers from the Stagger code and from the Ramses code. And therefore, it would be a misnomer to call this a code. It's a framework code inside. And there's some scaling information. And the flatness of these curves basically shows that it scales indefinitely. And you can notice that the y-axis is of the order of 1 microsecond per cell update. And that was the situation in 2018 for hydrodynamics. Nowadays, it's the same for magnetohydrodynamics. Strong scaling indicates that if you have variable number of resources, for example, if somebody gives you 100 million CPU hours, you're actually able to run it in the allocated time. So it's important that it's able to scale with the number of cores on a fixed size problem. So now to the question, why is it the code framework? A code framework turns upside down the relation between the solver and the services. A normal code works like this. It has some kind of main program, and then it has input-output, and it calls MPI services, calls a Riemann solver, and calls atmosp services, and so on. You turn that upside down and you place the solver in the middle. And you don't give it any other responsibility than to do what it does, namely take a time step. So it's basically the paraphrasing, don't call me, I'll call you thing. And a solver basically has only 2 jobs. It needs to decide a time step, looking only at the local variables. And it needs to update the variables with 1 time step, and then just return. It gets called again to update the next time, but that's of no concern to the solver itself. It can forget about MPI. It can forget about parallelizing. It doesn't need to parallelize its loop because it's full of work together with its other sibling tasks being updated at the same time. So it would be overkill to try and parallelize the code itself. And that makes it very easy to implement an existing solver or a new solver. It doesn't have to worry about things like OpenMP or MPI. So the way this works is that on an MPI node, on an MPI rank, you have a number of tasks. And here they're labeled I, B, and V for internal, boundary, and virtual. So the internal tasks don't have any neighbor that's on a different node, on a different rank. The blue boundary tasks need information from a different rank, but they don't get that information as a detailed piece of boundary cells. It gets it simply from the fact that the boundary cells of that other node exist in a copy. And we call these virtual tasks. So the virtual tasks are simply mirror images of tasks on other nodes. And this simplifies programming a lot because you don't have to do anything special for tasks that are on the boundary. They can just pick their values that they need from the task that is next to it with exactly the same code that it would use internally to get neighbor information. There's a circle of things going on. A task is selected for update. It's prepared in the sense that the framework will load its guard zones. Then it does its update. And then the framework looks at the consequences. And what are the consequences? Well, if this task is needed by another task that was waiting for this update, then the consequences that that task became updatable, and it gets put onto the queue from which the dispatcher picks tasks to be updated. from this organization is that it's extremely simple to load balance. If you find that one task has too much work to do, you can just give its a few of its tasks to a neighboring rank by simply switching a bit. It's going to send it to the neighbor anyway, because they send boundary tasks, exchange boundary tasks all the time. And the only thing that needs to happen is that they change ownership. So that's how ranks collaborate in this scheme. And that load balancing is also completely local in logical space. So this comes from taking a space-time view. It's sort of an adaptive mesh refinement in space-time instead of space. And we've had a number of spin-off innovations coming from this space-time view. For example, moving meshes. Now, when we do models of accretion disks, we are working on a mechanism where the patches are organized in cylindrical shells and they're rotating with a local Kepler speed, which means you can take time steps that are much, much longer, because we are, for example, right now moving with 30 kilometers a second around the sun, but the sound speed in the early protoplanetary disk of the solar system was only about 1 kilometer per second or so. So one gains a factor of 30 by moving around with the Kepler speed. Another invention is to have something that sounds as a contradiction in terms, stationary Lagrangian meshes. But that means that you have a mesh that is allowed to move one cell, and then you move it back again. So you arrange to have a Lagrangian bulk speed that exactly fits the motion of one mesh point per time step. And then you can sort of subtract huge bulk velocities this way. Another offspring is an adaptive n-body solver. If you look for n-body solvers, talks about that, you'll find Volker Springer's talks on the net, and he always has this illustration an adaptive n-body solver because it's very difficult to make it reflective in time. However, because you have this space-time view and you have snapshots, you have these time slices, you can make very precise predictions of where the particle will be in the next time step. And if you then choose the location to be half a time step forward in time, then you can make the update time reflective. And that's what's needed in a symplectic solver. So then you can make it adaptive. Another multitask thing is to have separate field and particle solvers. And the funny application is the so-called Mulligan module, where if you have, for example, a cold interstellar medium cell, which takes large time steps, and suddenly a supernova goes off nearby, then that time step may turn out to be too long and you may need to make a do-over. And a do-over in golf is called a mulligan. So that's why we got the name from. And in this case, it's very easy because we have the time slices. We just discard the last update and say, okay, we need to do it again, but with a much shorter time step because the neighbor is doing something wild. So now over to another angle on this. Namely, what can we do when we have this revolutionary gain in capacity? Well, we can fix the problem that we saw from the beginning, that we can't really think of a solar active region without thinking of its context. Where does it come from? Where do the magnetic fields come from? Well, you have to think of the whole convection zone, but then what do you think of then? Well, you think of active region periodicity and the solar cycle and so on, and you have to think in completely other scales in space and time. Can one even do that? Well, one can actually, by using a special technique. We started using this technique in star formation. So that's where I can most easily illustrate it. And you can also look at these papers, which were not done with the dispatch code, but with the Ramses code. But the idea is the same, and one can do exactly the same with solar simulations. So, for example, in the context of giant molecular clouds, with a resolution of, with a size of a few parsecs, so 10 million astronomical units, one can afford easily a timescale of 10 million years. In other words, you can actually simulate a giant molecular cloud creation and destruction. But if you go to, instead a resolution or a size of 10,000 IAU, which is sort of the core size out of which a star system is formed, then you can perhaps only afford 100,000 years. So you select a time window where something interesting happens, and you use the larger scale as a background, a context. It was the context that created this particular star formation event. And you can do the same thing again. That thing will form a protoplanetary disk, which will mediate accretion to the star. The star has to get its mass this way through the disk. And it starts out somewhere between 10⁻⁵ and 10⁻⁴ solar masses per year, and drops down rather quickly within 100,000 years to something more like 10⁻⁶ or so. So now you can decide, I want to study the first 1,000 years. You find perhaps some hourglass geometry. You can study another time frame for 1,000 years, where you find perhaps jet formation, and you can form a late context with perhaps azimuthal magnetic field dominating. So that's the idea of zoom simulations. And you can, of course, do exactly the same in the context of stellar atmospheres. If you want to study a few hours of evolution in a solar active region, well, first you have to have the solar active region, which means you have to have some dynamics going on for weeks or months, driving from a source that comes from below, that comes from something that happened over months to years of time scale. And you can do exactly the same thing. You model first the large time scale, and then you zoom in time and space to whatever you can afford. And the sun is an actual display case. It's a perfect benchmark. Because if you think about it, it's really the only object in the universe that gives us a detailed time-resolved 3D display of dynamics. Here's a movie showing observations. It could really nowadays be a movie showing simulations. It's hard to tell the difference nowadays. But if we compare to this, what's this? Well, this is a picture of dust in the Orion Nebula. It's extremely dynamic. There is a supernova shell here, for example, and everything is evolving on the time scale of dynamical time in this image. We have no chance to see it because we only see a snapshot, because we have short lives as human beings. So we can only observe a snapshot of this. And that's really irritating. It makes it very difficult to compare. Whereas in the solar case, we can really compare also the time information. So then the challenge is, well, we can try to understand solar active regions as we've been doing for a while. And even worse, we can try and understand the heating and dynamics and diagnostics of the chromosphere and corona with solar flares and coronal mass ejections. And there we simply cannot avoid doing it with a context. We really need to model a global hierarchical space-time context to get this right. So now I'm going to show you how I can model a spherical object with Cartesian boxes. The one way is to put the whole thing inside one box. But the other one is to build up a spherical object with small Cartesian box. It's a really good idea to think in terms of a volleyball. If you remember how a volleyball is built, it has 6 faces, all identical. And you can construct them with Mathematica, for example, by taking the octant symmetry directions marked by rods here, and you add a surface. It's bounded by constant z longitude, touching those rods here. So you'll see here it's a constant latitude, and it's a variable in longitude. And then the other direction is bounded, of course, by exactly the same thing spanned by these 4 rods. So you add the other surface like that, and you add one there and one here. And after adding all 6, you get a volleyball. Here, the gaps and an ionosphere, which is blue, has been added just for clarity to indicate where the seams are. The seams could be perhaps some problem, but let's first look at the scales here. So let's take one of Bob Stein's largest magneto-convection in a box simulations projected on the front here. It's 192 megameters square. You would need actually 35 of them to cover one front section of the volleyball. And since there are 6 of these, we conclude that this rather huge simulation covers actually only about 0.5% of the solar surface. So wouldn't it be really expensive then to do the whole thing 200 times more? Well, let's first look at what this really means in terms of size. Here's the zoom in to the box simulation, and you can zoom in once again, and you get to the surface dynamic scale, which is about 100 times smaller. And do it in a context which may not be working on Zoom, perhaps, but I'm just going to go through it nevertheless. And then we come to the first problem. Such a box is flat, so it's not really following the surface. And it doesn't really fit. So in order to make it fit along the upper edge, for example, you have to tilt these exactly cubical boxes a little bit. But as long as you have many of them, they must be small. And this tilt is really only a very small effect. And you can treat that effect exactly correctly by maintaining inside the cube the exactly correct direction of gravity to the source. And whenever you interpolate to get the guard zones in one box, you do it correctly in such a way that you transform the velocities. A velocity that is exactly in the x direction in one box will be slightly in the y direction in the next box. And you take that into account, and then you have something which is a representation of a sphere by hundreds of thousands of little boxes that all are Cartesian. And having them Cartesian has a huge advantage compared to using, for example, spherical geometry. Namely, there aren't that many good solvers for spherical geometry. You're bound to then use just a few very specialized ones. But if you have a Cartesian box, you have hundreds of solvers to choose from. Now, let's look at the performance penalty. And here's a number of patches next to each other. You can see their size would be roughly the ones that we started out using for granulation, so about a few megameters on the side. That would be suitable, actually. And one could always then use AMR, Adaptive Mesh Refinement, to zoom into smaller scales. So what about the corners then, where things really overlap badly, like here? Well, in a normal solver, that would be really difficult to cope with. But if you think about this patch, time evolution, those patches don't really overlap because they don't overlap in time. So you can actually update one and then use that information in another one that overlaps, and they overlap in space but not in time. So that doesn't create the conflict. And you can actually cope with corners also like that. So to sum up, by populating this volleyball geometry with Cartesian patches, one can easily represent one layer. But let's look at what happened, and let's look at if it's affordable. So here's a plot of the sun speed in the sun, taken from the standard solar model, Model S from Christensen Dalsgaard in Aarhus. And if you look at the acceleration of gravity, it looks like that. If you combine the two, you get the pressure scale height. And notice how it really is dramatically dropping only at the very surface. So through most of the convection zone, the pressure scale height is actually much larger than in the surface layers. So if you now specify that you want a number of cells per pressure scale height, then you can easily make a plot of the minimum number of cells per layer that you need. The scale here goes to 10 billion, 10 to the 10, but that's okay, that's affordable basically. And if you zoom in, I zoom into the surface to show you how enormously steeply this increases towards the surface. So if you want to make a cheap model and, for example, to develop a solar dynamo simulation, you can do that by stopping a little bit below the surface. That's been a common technique in modeling solar convection in a global context for a long, long time. But the difference here is we want to do it in a zoom context. So this is the cost per unit time in arbitrary units. But if you do it in real units, you can find out that the accumulated cost is actually only of the order of 50 core hours per solar second. So on a reasonably sized, medium-sized cluster, you can actually do this at base resolution. And then if you want to do it more carefully and more in detail, you can go to a larger machine. You can actually even do it on a laptop. I have a laptop and I can actually run this simulation on my laptop. It covers 0.6 to 0.95 solar radii. One could include smaller radii, but that would be sort of, it would be cheap, as you could see in the previous ones, but also pointless, except if I want to study G modes. So because we're not going all the way to the surface, instead we can do Newtonian cooling, calibrated to give the right solar flux. And in this case, you need about 16,000 patches to cover the whole thing. So about 68 million cells and 24 gigabytes of memory, not too bad. This laptop has more. And you would then set the whole thing in motion by starting with the solar Model S. Here's a zoom in of the larger and larger things you could and here's an actual snapshot of the initial state where you have no velocities, but you have a density and internal energy. That gives you a pressure, which is presumably giving you a balance with the pressure force. In practice, it wouldn't, not exactly, because this depends on the equation of state. And the correct way to handle that would, of course, be to reiterate, to solve the hydrostatic equilibrium equation with this exact equation of state, so that it would be an exact balance when you start. And now a very, very important detail, or actually more than a detail. What solvers should we use for this? The standard choice would be to use a Riemann solver, and people would then immediately say, why would you need a Riemann solver for this? A Riemann solver is known to be good for things with shocks. It would be pointless to use it here when things are extremely subsonic. Well, there are several good reasons. And you can see them in the red Bible about Riemann solvers, where Toro has some figures showing the difference between HLC and HLL. The difference being that the C and D variant of the Riemann solver can represent a jump in density with no jump in pressure, a so-called contact discontinuity, exactly, without any diffusion. So we can keep density jump without any diffusion for an indefinitely long time, provided that there is no motion. The same picture, the same figure in the book also shows that it starts to diffuse, of course, as soon as you start moving it. So therefore, this kind of solver explicitly violates a basic principle of dynamics, namely Galilean invariance. It does not give the same answer for a moving system as for a stationary system. That would normally be considered a drawback, but here it's the main advantage. Because what has been the problem with all previous simulations of the solar convection zone? Well, they had to do all kinds of tricks with the sound speed, for example. One reason, and perhaps is that it's too expensive to use the full sound speed. Well, the plots I showed previously were using the full sound speed, and that did not become more expensive because of the way dispatch uses local time steps. But a much more important reason, actually, for using a reduced time step scheme is that most of these solvers that have been used in the past have a diffusivity, which is proportional to sound speed. And because these speeds in the deep convection zone are highly subsonic, the numerical diffusion is always, or the numerical viscosity is always much larger than the real one. So that's the point. That's the reason why a Riemann solver would really be perfect here, because it can go to very, very low diffusivity. And the current update cost is still only of the order of 1 to 2 core microseconds per cell. Andres Popovas in Oslo is developing an interesting variant of this, namely a Riemann solver based on entropy instead of total energy. And that's really, really important at the surface where magnetic field starts to dominate the total energy, and you quickly get a problem with a solver that uses total energy. So with this, we hope to attack the so-called convective conundrum, which consists of observations and simulation not agreeing on what the convective speeds are in the deep convection zone. So scaling here is the key. In the case of traditional codes, cost scales, of course, as the sound speed divided by the resolution to the 4th power, and that increases with depth because the sound speed increases with depth. And that forces one to use the reduced sound speed trick. With dispatch, on the other hand, if patch size is proportional to scale height, then the cost scales with the sound speed divided by the scale height to the 4th power, and then it drops dramatically with depth instead of increasing. So you can actually afford to have an increasing resolution in terms of patch size relative to pressure scale height, and still have an affordable simulation where reduced sound speed is not needed. And just as an illustration of how easy it is to implement an experiment, this particular experiment with the volleyball geometry requires only these extra files. It's a slightly different main program, which is 11 lines, and then it has a 240-line code that sets up initial conditions, basically interpolating in Model S, etc. This batch code connects to services like forces and cooling and stuff using an extras module, which is really just train station with couplings, and it consists only of calls. So here it calls, for example, the forces, it calls the cooling, etc. Okay, it needs a force of gravity, which doesn't exist before, so that's 100 lines. And it needs model 1D thing to interpolate, that didn't exist either. So altogether, this is like a small number of extra codes that are needed for this particular experiment. So now let's look briefly at radiative transfer, because that's, of course, really, really key when we want to model stellar atmospheres. And it's usually thought to be quite expensive. It doesn't have to be, because the radiative transfer, especially when written in terms of net radiation intensity, difference between intensity and source function, is extremely simple and extremely cheap. And if one writes it like that, then it goes to the correct diffusion limit at large optical depths without numerical problems. So in order to solve that, the simplest method is to have a solution and then advance it one layer. To advance it one layer, you want to ask for the intensities at the grid points. And to do that, you need the intensities at the previous layer, which you can interpolate to get. And you need the opacities at these 2 points. And if you want to do it with a higher order scheme, you need 3 layers. 3 steps: compute source function and opacity, interpolate to get the start and end points, and solve the radiative transfer equation. That's cheap. It costs 10 nanoseconds per point, per angle, per opacity bin. And most of those 10 nanoseconds is simply table lookup. Table lookup to compute the source function and the opacity. So radiative transfer is extremely cheap. And therefore, you can afford about 100 angle opacity bins without more than doubling the cost of a simulation. And of course, since things are diffuse, you don't need that many angle points. In the case of protoplanetary disks, you need to have point sources, and that can be handled in basically the same way with basically the same cost. An important other technical detail here is that you don't have to solve the radiative transfer and the MHD using the same time step. The group in Oslo has been doing this for a long time. They solved the radiative transfer on a much longer time scale. And part of the reason then is, of course, that they are forced to use an extremely short MHD time step. So in my case, in our case, when we are not forced to do that, perhaps it would be the other way around. Maybe you do the radiative transfer more quickly, more often than the MHD. But the important point is they don't have to be the same. These are independent tasks or semi-independent tasks and can be solved independently. Let's just very briefly also mention how to do because you can't really understand the corona with its particle acceleration without doing particles. We've done that before some years ago with Gisela Baumann as a PhD student. We started out from a SOHO magnetogram and used a cutout like that, which had a parasitic polarity, and we started from that and moved the field lines around with an MHD model. And then we take a cutout and treat that with particle and cell methods. So you connect the two with boundary conditions and you have context again. Because doing particle in cell simulations of the whole sun or whole active region is basically impossible. But you only need it in the neighborhood of critical points, null points or similar things where particles are accelerated. And we were able to use that to understand actually how particle acceleration works and why you get a power law. I don't have time to get into that. I just want to point out that there are lots and lots of applications for hybrid simulations, where you mix particles and arrays. So in this case, you combine the two codes and you have each one already existing. You can just choose between them and make a connection with boundary conditions and initial conditions. What is the cost? Well, as I said before, the cost of grid updates are about 1 microsecond per cell as a round number. And the cost per particle for particles is about 0.1 microsecond per particle update. You need 3,200 particles per cell to represent the Maxwell equations and charges and so on. So that would seem to indicate that there is just a factor of 10 speed difference between the two. But actually, you also have to take into account that the time step and physical scales are different. So in reality, it's more like a factor of 1,000. So it's expensive, and that's why one can do particle and cell simulations in a context, but only in a small fraction of space. And it's only needed in a small fraction of space. Let's also look briefly at planetary atmospheres. Here is a model that we did a couple of years ago. The round circle that you see here is supposed to represent Earth, but it's not Earth itself. Earth is smaller than the little pixel in the center. The ring here is actually the Hill sphere, and the Hill sphere is 240 times larger than the Earth. Its size scales in exactly the same way as the size of the Earth, scaling as a 1/3 power of the mass, but it's so much larger. And we see basically the scale height of the disk, the height over which the pressure falls by a factor of 1/e. So we model this with full resolution down to the size of the Earth embryo, which requires about 1 to 700,000 in scale ratio. And we did it with exactly the same zoom trick as before. We started out with a fake planet, which is 27 times larger than the real one, and used that to relax the pressure and the density around the embryo. And we then reduced the size to 9 times the real one and 3 times the real one, finally the real size. And each time you only need to run for a relatively brief time compared to what you did before. So this makes it affordable. The dynamic that you find is something called horseshoe orbits. Where I thought I had a slide showing that, but it comes later. So velocity on the inside is faster and velocity on the outside is slower. But if you're close enough to the planet, the Coriolis forces gas and dust to turn around and into a global shape that looks like a horseshoe, and therefore it's called horseshoe orbits. Here we use a fixed mesh refinement with a scheme that looks like Rubik's cubes. So the smallest Rubik's cube contains the Earth, and it's 2.4 times larger than the, it's 2.4 Earth radii, so it's slightly larger than Earth. The next layer has that cube in the center and then has 26 more cubes. And we refine with a factor of 3, not with a factor of 2. So if you do that, you need 7 of these layers, 7 of these hierarchy layers to get to the size of the scale height. And that's affordable because you do it in this zoom way. And you can then compute the dynamics of particles inside the Hill sphere. And that's really interesting because you find that the accretion heat of these small particles, we assume that the particles are basically chondrules of millimeter size, not big pebbles like decimeter size, which has been popular in the past, but we see no reason to just do something different than what we can observe in meteorites, where we see millimeter-sized particles, not anything else. And it turns out that this is a really good approach. So the structure of the atmosphere in the early solar nebula is probably quite close to isentropic. The reason being, are really two reasons. The optical depth, if we estimate the optical depth of the minimum mass solar nebula, is several hundreds at least. So it's isolated from cooling. And moreover, from the motion pattern, we can see that gas is exchanged. So this is a thing called recycling in this business. And that tends to maintain the entropy of the gas constant. So we can easily integrate the pressure equilibrium, assuming constant entropy, and we get something like this, either for ideal gas or for a better equation of state. The target gets actually so large that solids like silicates would evaporate. And the planet can only accrete by having a very dense atmosphere where the vapor pressure of silicates is reached, and solids basically rain out of this very dense atmosphere. That's the working hypothesis of how you get rocky planets to form inside a disk nowadays. And it's indirectly confirmed actually by observations, because there is a famous discovery of a so-called valley between rocky planets and super Earths. The pink part is rocky planets, and the blue part is super Earths and mini Neptunes. And there's a minimum between them, and there's even a dependence on things one can find in papers. And this is understood as, at least from some people's perspective, as a consequence of evaporation of the primordial atmosphere due to the heat of the embryo. So I'm going to finish off here, but just indicate that using this that are observed indirectly from isotopic abundances. So the very same technique that was so beneficial in stellar atmospheres can also be used to treat planetary atmospheres. And if you think of the ratio of scale to size, it's much more economical to model planet atmospheres than to model stellar atmospheres, because they're much more compact. So I foresee that modeling of 3D planet atmospheres is going to be an expanding topic in the future. And the movie is showing just how important convection is in that context as well. So winding up, future applications. Many expensive problems can become affordable with task-based codes. If you think, for example, of non-LTE and scattering problems, in many locations on the sun in the solar atmosphere, for example, the radiation field will not change very much on a second time scale, on a few seconds time scale, or even more, because the radiation field is sensing source functions or source locations over a wide area. And that means if you're solving something like a scattering or non-LTE problem, you only need a few iterations to update the solution.
HÅAke?
And if you're doing partial
Professor
redistribution,
Nordlund?
the same thing is basically true.
Well, at least on my side, I'm not sure if I'm the only one, but I cannot hear you. I think you have lost your sound.
Oh, really?
The only one?
No, I hear him well.
We can perfectly see you, see your screen, but okay,
all right.
So it's my problem then. Sorry, then just go on. Sorry.
Let me change microphone on.
All right, so please go on. It's on my end for some reason.
How about now?
It's perfect. It's perfect. It's good.
Same thing.
It's perfect. It's good. Aki, we can hear you. Can you hear us?
Yeah, I don't know really how to fix that, but
It's back to normal on my side.
Everything is okay. Everything is okay.
Yeah.
Everything is okay, Aki. You can continue, please.
any sound coming through?
Yeah.
Yes, we can hear
Yes,
you.
it's perfect. It's perfect.
Okay. Now I can't hear you on the other hand. Huh? So as I was showing, I'm already on the summary slide, so we don't really have that much to but the problem is I can't hear you now, so I can't hear the questions. Maybe I should try and change to my iPad, which is usually more reliable than my laptop.
Maybe if you go
Just a
back
moment.
to, yeah. If he goes back to how it was before, it was okay, right? Let's see if he can read on the chat.
Yeah. I think, well, I think the sound is back to normal, at least on my side. Kati, I'm not sure about you. Can you hear well?
I can hear perfectly, yes.
Yeah, I think everything is back to normal. So if you want, we can proceed with the questions the way you prefer.
But if he doesn't hear, Aki, can you hear me? How is he going to answer the questions, right?
Maybe we can use the chat.
Let's use the chat, yeah, but it's weird.
Okay, so maybe if he went back to the same way it was before, he could hear us, right?
I'm not sure if he can read easily the chat if he's sharing a screen, by the way.
But he's not sharing the screen anymore.
Okay, then he should be able to.
He's not sharing the screen.
Okay,
Yeah.
So they should be able to hear the chat.
Yeah, okay, anyways, I'll just say thanks, Aki, for a great talk and for showing us that transformative gains in computing capacity can be achieved. It's very hard that he can't hear us, but so we'll try to do the questions session in the chat instead of people asking questions directly, unmuting themselves. So we can start. If there are any questions, please, you can put on the chat. But I'm not sure if he can read the chat either. Let's see. Aki? I'm asking if he can read the chat. Let's see, because if he can't read the chat either.
That's very odd. Hello?
Aki, can you hear us?
No?
Hello? Aki, can you hear us?
Oh, he's
How
in
about
the
now?
Yeah.
Yes. No, and I think we can hear you. Well, yes.
We can hear you. Okay, so.
So let's try to leave things as they are now.
Yeah, okay, so I just want to repeat that.
I can hear you too now.
Okay, so there's some echoing, so maybe you want to turn one off.
Like that. Okay. Now I can hear you.
But can you turn one off so that we don't have echo?
Yes.
Hope that it's gonna.
I need to find my. I can simply jump off. Now it should be okay.
Okay, you're there. Okay, so thanks for a great talk. Applauses. So we can continue with the original plan. So we'll have a short discussion, and we'll start by asking if you have any comments or questions to Aki. And if you have a question, you can you can type on the chat, or you can also raise your hand and unmute yourself. So let's see if we have any questions. If not, I have one. Vern has a question. So Vern, go ahead.
Yeah, okay. Can you hear me okay?
Yeah, we can hear you.
Yeah, so Aki, I have a question. Do you think that this sort of approach could be applied more generally to problems on a galactic type scale? What I'm thinking of is, since you do such a good job of modeling star formation, would it be possible then to follow large populations of stars via something like chemical evolution? So you could do efficient galactic chemical evolution on fairly detailed or small scales. Would that be any advantage to this?
Yes, I mean, this approach is applicable in many contexts. It consists of two main parts. The fact that you can do local updates, and the fact that you can get context by doing some simulations from larger scale to smaller scales. There's an aspect I didn't touch upon, namely that most of the future machines which will offer capacity will be based on graphical processing units. And we have had a project that revealed how to work that out. We have a master student who was able to get really good performance on GPUs, and also importantly was able to show that one can get away with relatively small modifications of source code. That is really important because, for example, chromospheric and corona physics, as covered by the Bifrost code, needs a lot of extras physics codes. And if all of them had to be converted to explicit GPU code, it would be very difficult. But they can actually be run with OpenMP directives instead.
Okay.
Okay, thank you. So any other questions or comments? I have one actually that is related also to the galaxy. We are living in the era of large galactic surveys. Just to give an example, a survey like Apogee in Sloan 4 and 5 will, by the end of Sloan 5, have 5 million stars observed that we have to model. These are high resolution spectra. And currently we're doing like LTE, 1D modeling for most of it. And when do you think that it will be possible to do non-LTE 3D hydro modeling for such a large survey at some point soon? Do you think it will be possible? And what would be needed in order to achieve such an ambitious goal?
Yes, that's exactly what I was aiming at when I was rounding off with the last few slides. You may know Maria Bergeman. She will be spending a sabbatical here in Copenhagen to exactly do the implementation of non-LTE in stellar atmospheres. And I expect that this will really be doable on a basis where I can do thousands of models. And I can complement that with reporting that even with the much slower Ramses code, we now have simulations of star formation that contains about 3,000 stars. So with this speed up that we expect with the dispatch code, we can actually simulate number of stars ordering hundreds of thousands. which is necessary if one wants to have the context of star formation, because it's very variable. It depends on random chance. So we can't just have one model of star formation. You need to have a statistical correct picture.
Thank you. Gloria, you can go ahead, please.
Thank you. I was wondering, do you have any thoughts on the hydrodynamics in interacting binary stars when they come like in eccentric binaries, when they come close to periastron, and the type of atmospheric and outer layer effects? Can this be modeled with your methods?
I say I've thought about that, but surely you can, because you can actually model global stars with reasonable cost budget nowadays. So you can certainly model also interacting stars.
Thank you.
Any other questions? I have one that maybe doesn't make sense, but how about artificial intelligence and data-driven modeling? Because a lot of the large surveys are going this route, right? They do the real physics for a certain number of stars, and then they model with the physics, and then they do data-driven modeling for handling a large number of stars fast. Would that have any application?
I picked up the context, but I didn't quite see the question. What was the question?
The question is maybe it totally doesn't make sense, but just for the sake of the discussion, if there is some of the large surveys have tried or are trying or will try to do data-driven approaches, that you have training sets for which you do the real physical modeling, and then you train it on those results, and you do data-driven modeling for 5 million stars, let's say. That's the goal for Sloan 5, Apogee and Sloan 5. Does any of this, are there any gains that can be made from what you presented today in the field of artificial intelligence and data-driven modeling?
Certainly, because if you want to make an artificial network that can match observations, you need to have a training network also. So if you can do sufficiently realistic modeling, then you can also train the network to come to the right conclusions. And conversely, if your network doesn't work to get the right conclusions, you know there was something wrong with your training network. So those two are closely coupled and can certainly benefit from each other.
Thank you. Any more questions or comments for Aki? If not, Aki, it's close to 10:20 here in Tucson, and whatever time 20 for you guys. And I thank you very much for a great and inspiring talk. And I'm looking forward to the future where all these simulations can do things so much faster for us. Thank you so much.
Well, thank you. And I'm sorry about the technicalities that were a little bit unfunctional at the end here. Fortunately, only at the end.
It was perfect. Thank you.
Thank you.
Thank you. Thanks very much, Katja. Thanks very much, Åke.